In section 3.6, we are going to look at some examples of applications of information diagrams. To obtain information identities in an information diagram is what you see is what you get. To obtain information inequalities, we distinguish two cases. First, if mu star is non-negative, then if a set A is a subset of a set B, then mu star A is less than or equal to mu star B. This is because mu star A is less than mu star A plus mu star B minus A, because mu star is non-negative. Now A and B minus A are disjoint, and so by set additivity, this is equal to mu star A union B minus A, which is mu star B. Therefore, we have shown that if A is a subset of B, then mu star A is less than or equal to mu star B. If mu star is a signed measure, then it is less straightforward, and we need to invoke the basic inequalities to compare mu star A and mu star B. In example 3.12, we are going to show the convexity of the entropy function. Let x1 has distribution p1x and x2 has distribution p2x. Now we define new random variable x with distribution px equals lambda p1x plus lambda bar p2x, where lambda is between 0 and 1 and lambda bar is equal to 1 minus lambda. That is, px is a mixture of p1x and p2x. We are going to show that entropy of x is greater than or equal to lambda times entropy of x1 plus lambda bar times entropy of x2. Consider the system as shown, in which the position of the switch is determined by a random variable z, with probability z equals 1 equals lambda, and probability z equals 2 equals lambda bar, where z is independent of x1 and x2. Now in the system, the switch takes position I if z is equal to I, that is, if z is equal to 1, the switch is up, and when z is equal to 2, the switch is down. The random variable z is called a mixing random variable for the distributions p1x and p2x. Then, x has distribution px equals lambda p1x plus lambda bar p2x, as required. Now from the information diagram for the two random variables x and z, we see that x tilde minus z tilde is a subset of x tilde. Because mu star is non-negative for two random variables, we can conclude that mu star x tilde is bigger than or equal to mu star x tilde minus z tilde, which is equivalent to entropy of x is bigger than or equal to entropy of x given z. Now entropy of x given z is equal to probability z equals 1 times entropy of x given z equals 1 plus probability z equals 2 times entropy of x given z equals 2. Now probability that z equals 1 is equal to lambda, and probability z equals 2 is equal to lambda bar. Now entropy of x given z equals 1 is equal to entropy of x1, because z equals 1 means that the switch is up. For this situation, x is equal to x1. Likewise, the entropy of x given z equals 2, that is when the switch is down, is equal to entropy of x2. This proves inequality 1, and this shows that entropy of x is a convex functional of px. The interpretation of this inequality is that the entropy of a mixture of distributions is at least equal to the mixture of the corresponding entropies. In example 3.13, we are going to show the convexity of mutual information. Specifically, let the pair of random variables x and y have joint distribution pxy, which can be written as px times py given x. We are going to show that for fixed px, Ixy is a convex functional of py given x. Let P1y given x and P2y given x be two transition matrices representing two channels. Consider the system as shown, in which the position of the switch is determined by a random variable z, as in the last example, where z is independent of x. That is, the mutual information between x and z is equal to 0. So, when the switch is up, x and y are connected by the channel P1y given x, and when the switch is down, x and y are connected by the channel P2y given x. In the information diagram for the three random variables x, y, and z involved in this problem, we let Ixz given y equals a, which is non-negative because this is a conditional mutual information. Accordingly, we have Ixyz equals minus a, because Ixz is equal to 0 by our assumption. Recall that the probability that z is equal to 1, that is, the switch is up, is equal to lambda, and the probability that z is equal to 2, that is, the switch is down, is equal to lambda bar. Then, Ixy is equal to Ixy given z plus Ixyz. Here, Ixy given z is shown in the information diagram in blue, and Ixyz is shown in the information diagram in red. Now this is less than or equal to Ixy given z because Ixyz is equal to minus a and hence is negative. And we further write this as probability z equals 1 times mutual information between x and y given z equals 1 plus probability z equals 2 times mutual information between x and y given z equals 2. Now the probability that z is equal to 1 is equal to lambda, and the probability that z is equal to 2 is equal to lambda bar. The mutual information between x and y given z equals 1, that is when the switch is up, is equal to the mutual information between the input and the output of a channel, with px being the input distribution and p1y given x as the transition probability. Similarly, the mutual information between x and y given z equals 2, that is when the switch is down, is equal to the mutual information between the input and the output of a channel, with px being the input distribution and p2y given x as the transition matrix for the channel. Thus, we have shown that Ixy is a convex functional of py given x. The interpretation of this result is that for a fixed input distribution px, the mutual information between the input and output of the system as shown, which is obtained by mixing two channels, p1y given x and p2y given x, is at most the mixture of the two mutual informations corresponding to p1y given x and p2y given x respectively. In the next example, we show the concavity of mutual information. Specifically, let the pair of random variables x and y have distribution pxy, which again written as px times py given x. We are going to show that for fixed py given x, Ixy is a concave functional of px. Consider the system as shown, where the position of the switch is determined by a random variable z, as in the last example. Here, when the switch is up, x takes the distribution P1x, and when the switch is down, x takes the distribution P2x. In this setup, when x is given, y is independent of z, because the channel output y depends on the position of the switch only through the channel input x. So z, x, y forms a Markov chain. As we have seen before, for a Markov chain, mu star is non-negative, and the information diagram for x, y, z is as shown. From the information diagram, we see that x tilde intersect y tilde minus z tilde, which is shown in blue in the information diagram, is a subset of x tilde intersect y tilde, which is shown in red in the information diagram. Because mu star is non-negative, we immediately see that ixy is greater than or equal to ixy given z, which is equal to probability that z is equal to 1 times ixy given z equals 1, plus probability that z is equal to 2 times ixy given z equals 2. Now the probability that z is equal to 1 is equal to lambda ixy given z equals 1, that is when the switch is up, is equal to the mutual information between the input and an output of a channel, with P1x being the input distribution and Py given x being the transition probabilities. Likewise, the probability that z is equal to 2 is equal to lambda bar, and ixy given z equals 2, that is when the switch is down, is equal to the mutual information between the input and an output of a channel, with P2x being the input distribution and Py given x as the transition probabilities. This shows that for fixed Py given x, ixy is a concave functional of Px. The interpretation is that for a fixed channel, by mixing the input distribution, the mutual information between the input and an output is at least equal to the mixture of the corresponding mutual informations.